Hello everyone, and thank you for joining. So welcome to the fourth seminar in the series organized by the Center for Technology Foresight and Policy (CTFP) at IT Jodhpur. So it is our pleasure to have Dr. Vallabha Rikka as our speaker today. So Dr. Rikka is a research scientist at the Electrochemical Safety Research Institute (ESRI) under the UL Research Institutes based in the US. Dr. Rikka is renowned for his expertise in developing safe and efficient fast charging techniques for lithium-ion batteries. Dr. Rikka's work has been instrumental in advancing the battery technology in the EV sector, that is the electric vehicle sector. He is a former scientist at the ARCI Chennai's Center for Advanced Energy Materials, CAEM, and he has a rich history in electric vehicles and the energy storage applications. Moreover, in the recent years, Dr. Rikka has extended his research focus to encompass the promising field of green hydrogen technology as well. That is basically moving beyond electric vehicles, right? So, with that brief introduction, let me welcome Dr. Vallabha Rikka. And thank you very much for joining, Dr. Vallabha. And it is a pleasure to have you today. And I think you can start with your presentation.
Yeah, sure. Yeah, good evening and good morning, everyone. Thank you, Dr. Vinod, for kind introduction and giving me this great opportunity to describe about the lithium battery or battery technology advancements for electric vehicles and its for powering the future. Am I audible, Vinod?
Yes, yes, very
Yeah,
much,
yeah,
please.
yeah. Thank you. Yeah. So, okay. Yep. So today, the transportation sector consumes more than 60% of uh, gasoline among all other sectors and releases the greenhouse gas emissions. If you can look at the usage and then demand over the past few decades, it is increases tremendously. As a result, we can see increase in temperature over the year, and which can actually resulted in global warming as well as affecting the living beings on planet. So if we can use the lithium battery technology and green hydrogen technology to integrate it to the transportation sector, along with using the renewable energy resources or energy storage grid technologies to these all lithium battery as well as hydrogen technology, this effect can be ultimately minimized. So today we will mainly focus on the electric vehicles technology using this lithium battery technology, how it is you know impacting or improving, it can contribute to the transportation sector. So before driving into today's focus, I would like to introduce about my current organization. I work at Underwriters Laboratories, commonly known as UL, Underwriters Laboratories, we can call it. And then this UL Underwriters Laboratories has three main centers, non-profit, like such as UL Solutions, and non-profit organizations like Research Institute, and then Standards and Engagements. All three institutes' common mission is bringing the world more safer. That is a common mission for all of us. And in UL Research Institutes, The Electrochemical Safety Research Institute is led by Dr. Judy Jivarajan. So she formerly worked at NASA over the 20 years, and then she contributed a lot for the battery safety technology. And then here our main focus is to uh, study the safety from the materials levels to the device level, and not only for the lithium ion battery technology, and we are expanding to beyond the lithium ion batteries, for which we are collaborating with various national labs and academic institutions, nationally as well as internationally. And recently we also funded the projects from DOE, Department of Energy, from the US government, which is like the program, call it as a ARPA-E program. So here mostly we are working on different applications. For example, materials levels to like energy storage devices like a lithium ion battery, solid state batteries, and their recycling, and then improving the safety at different operating test conditions, as well as developing the green hydrogen catalyst, and then their safety at materials levels to the large scale level. So these all parts we are working at our ESRI, like Electrochemical Safety Research Institute at USA. So let's dive into our today's talk. If we can look at the lithium ion battery technology, it is well deployed into the small scale technologies like mobiles, even watches, wristwatches, or smartphones, to the it developed integrated to the large scale systems like electric vehicles. On the other hand, if you can look at this technology, which requires the long operating time, like a duration, as well as the quick charging. And when we are doing it, when we are implementing the quick charging, the safety is involved for this technology. So today's our focus is to understand the battery technology from the mechanism, and how we have implemented or developed the fast charging methods by understanding the aging mechanisms of lithium ion battery at various operating test conditions, and then how we have mitigated those aging mechanisms, which I'm going to cover in the coming slides. So probably everyone aware of the lithium ion battery working mechanism, but who are like willing to, or who are very new to this field, for them I would like to spend a little bit time for uh, describe about the fundamentals on lithium ion battery technology. So if we can look at the lithium ion battery, consists three main components: cathode and anode and electrolyte system. And this cathode and anode are separated with a polymer, insulating polymer, which is also known as separator. So when we charge the lithium ion cell, the lithium ions are moves from the cathode to anode through the electrolyte medium, and then the slowly the cell potential will increases. Similarly, during the discharge process, again the stored lithium ions moves from the anode to the cathode side. So this entire process we can call it as a charge and a discharge. One charge and one discharge we can consider as a one cycle. So based on these number of cycles, the lifetime of the lithium ion cell will be defined. If you can clearly observe here, before the charging the lithium ion cell, before using the lithium ion cell, or before integrating the lithium ions into the anode, we can see here two interface layers are formed, which is also known as solid electrolyte interface or electrode electrolyte interface layers, which are not designed before constructing the or fabricating the lithium ion cell. These layers forms during the electrochemical cycles. So these layers are very sensitive and delicate, and which determines the rate performance and the safety of the lithium-ion cell at the different operating conditions. So, which we will discuss in our further slides. Today in the market, if you can look at this lithium-ion cells, for lithium-ion cells, there are different cathode and anode materials were actually developed, and some of them are in commercialized, some of them are still in the laboratory R&D conditions. And these based on the potentials of each materials, the cell energy density as well as the power density will be defined. And then the cell performance is mainly dependent on the operating test conditions. For example, we can say the charge discharge rate, what current rate we are giving, or how long we are charging, or how long we are discharging, as well as what operating conditions we are applying, or we are operating the cell. That is also influences on the cell performance as well as the safety. And then at what operating voltages, what level, what lithiation level or charge levels we are operating the cell, that also influences on the cell performance and safety of the device. But coming to the electric vehicles, which demands in a more precise way, like we can say, like the cycle life of the lithium-ion cell should be high while we are utilizing the high energy density from individual cell at fast charging. So this is very critical condition, because when we are operating the lithium-ion cell, we can, for example, we can consider the simple uh, chemistry, the LiFePO4 lithium iron phosphate with the graphite as a anode combination, if we can consider. So when we are charging, which means the lithium ions are removing from the lithium iron phosphate and inserting into the graphite electrode. So this process occurs simultaneously, which means when you are removing the lithium ions from the cathode, and we are inserting into the anode side. And if you can consider, if you can look at carefully, the deinsertion and the insertion of these lithium ions into the materials are having different mechanisms and different processes. So for example, in the anode side, the lithium ions, when are intercalating into the graphite, which will transform into different lithiation phases. Over the lithiation phases, it can actually changes the volume also over the lithiation process. So which can actually hinders the initial formated SEA layer on the surface of the anode. So when we are operating this cell at even at fast charging, and these effects even will be more effective. So it can actually reduces the performance of the lithium ion cell even faster. So if you can consider the overall spectrum of the involved aging mechanisms within the lithium-ion cell, which are many. If you can consider at the SEA layer itself, the SEA layer breakdown, SEA layer decomposition, and then SEA layer degradation at different operating conditions. Similarly, the electrolyte decomposition and then gas formulation. And at the interface of the cathode and electrolyte, if you can look at the oxygen evolutions from the cathode surface at a different operating conditions, and as well as the delamination and dissolution of the cathode materials can occur. But these all mechanisms, whether it is happens at an individual at a particular operating test conditions, or whether cumulatively these effects are happening within the cell, which is a very interesting and a very challenging for improving developing the new test methods for the lithium cells in order to improve the safety of the lithium cell. So if you can summarize in a tabular form, the cell aging, the whatever the aging mechanisms are taking place, which are influenced by the aging test conditions, for example, operating temperature or operating voltages. For example, we can say SOC, the state of charge, and depth of discharge, how much charge we have removed from the anode, or how much charge was stored in the anode, which also determines the, like, that test conditions also determines the cell performance, and then it can triggers the different degradation mechanisms. If you can look at the overall degradation mechanisms which are not directly related to the one particular test condition, it will be like it can induce by various test conditions, which is why we need to understand the aging mechanism, particularly for at particular operating test conditions, which can actually helps us to determine the particular test methods. And these all aging mechanisms, again, we can classify it into three different modes. For example, we can say the increase in the cell impedance is one kind of degradation mode, and whereas the loss of lithium inventory from the electrode materials and electrolyte systems, that we can consider it as one degradation mode, and as well as the loss of active material from, for example, the cathode material dissolution or delamination of the anode materials, those also comes under this category, these aging modes. And these degradation modes, we can like affects the, either it is in a capacity fade, which means we can say whether we can operate higher energy density or not, even power fade, whether we can quickly charge the mobile or not, or quickly charge the battery or not. That kind of degradation mechanisms we can classify into the we can classify them. So if you can consider for electric vehicle applications, the electric vehicle requires the high energy density to meet the long driving range, and then even we want to improve the fast charging, means we want to increase the C rate capability. If we can able to quick charge, which means the quick charge we have defined like 15 minutes of charging of the cell with a 100% of SOC or 100% of DOD discharge. So in this regard, the operating voltage ranges or SOC or DOD ranges we have considered like 80 to 100% will be the optimum for the electric vehicle applications. The similar way, the depth of discharge, like the driving range, supposed to be off between the 80% of DOD, which can actually improve the battery performance as well as safety. So based on these three constraints, operating test conditions, we have defined the design of experiments for defining the optimum fast charging test method. So if you can look at here, this lithium-ion cell we consider as a two water tanks. Like for example, cathode has a one water tank, and if it is a filled water tank, then anode will be empty water tank. So how we are filling the another water tank with this filled one, and how you are even refilling the water into the first can, that will be defines the, you know, the aging mechanisms. So in this case, like for example, how much charge you are keeping into the graphite, that can depends as the state of charge, and how much charge you are taking from the charged graphite, which defines as the DOD. So as I mentioned here, the for electric vehicle applications, the SOC and the DOD we are considering between the 80 to 100 to improve the to implement this battery technology to the electric vehicle systems. And based on these combinations, we have defined into four categories. One is like a fully charged and a fully discharged test condition. The second one is fully charged with the partial discharge, and then partial charge with the fully discharged, and partial charge with the partial discharge. So these four test conditions actually considered as a global test matrix, which means whatever the test condition you perform for the battery, which can comes under these four categories. So with this test matrix, we can easily identify what kind, like if you can run it, for example, at this test condition, so what kind of degradation mechanisms may occurs. So it is very easy to identify the aging mechanisms so that we can actually improve the battery charging protocols. So for which we have defined our test sequence of cycle life. So here initially we will do the capacity conformation test, and based on the capacity conformation test, and we will define the test matrix, how many test conditions we have incorporate for the identifying the aging mechanisms, as well as to understand or to determine the cycle life of the lithium cell. And then once you define the test matrix, then we will carry out the reference performance test, which will actually helps us to as a reference point for identifying the what level of aging mechanism it has taken or has occurred during the cycling conditions. And then after that we will go for the long cycles, continuous cycles, until reaches the 20% of initial its capacity. And once it reaches the initial means it reaches the 20% of capacity fade, then that cell we can consider it as a end of the life. And then after it reaches the end of the life, we can go for the failure analysis, like once you identify the failure mechanism, the main failure aging mechanism, and then that can easily helps us to it can helps us to mitigate the aging mechanisms over the long cycles. So for which we have procured the 100 numbers of commercial lithium cells for carry out this experiment. And then initially we have done the cell validation. We can say that cell validation comes under the category of reference performance test. And then after that we have done the after complete the cycle life, we will go for the failure mode analysis or failure mechanism analysis we will do. So for which we have done the we have carried out high power cycling unit for checking the long cycle life. So when we are conducting these experiments, we have to set up the operating safe test conditions, for which we have done the cyclic voltammetry analysis initially. So with this cyclic voltammetry, we can see that we can identify the what are the main redox reaction mechanisms are taking place within the cell, what operating voltage range, and whether we can still up to what voltage even we can operate this cell, that we can identify from this cyclic voltammetry analysis. And here we can see even this LiFePO4 based lithium chemistry, which has showed the prominent redox reactions between the, like for example 2.8 voltage to 3.6 voltage. Even if you operate the cell up to 4 voltage, we haven't seen any degradation mechanisms. So which can actually helps us to implement in our test conditions, because here we can say whenever we are operating at a different charge currents or a higher charge currents, we can see from the low charge current to high charge current, the voltage will be always drops or it will be reduces. When voltages will reduces, for example, if you can the discharge voltage is cut off to, for example, around 2.8 voltage, and then when you are operating this cell at a higher C rate, if you are maintaining the same operating limiting test condition, then what happens is this at this test condition, the obtained capacity will be lesser than that of the lower C rate test conditions. So that's why whenever we will perform this kind of cyclic voltammetry analysis, it can easily identify whether if you can reduce the operating voltage even below 2.5 voltage, whether the cell is going to under the aging condition or not. Like in our case, there is no degradation mechanisms were occurred even at the lower operating voltages. So we have included this limiting factor for high charge rate performance, so which enables us to get the fully we can utilize the fully the total available energy density from the lithium cell. So based on that, we have defined 9 test conditions. Here we can see each one. For example, in a first condition, full charge, full discharge condition, 100% of charge and then 100% of discharge of the anode and cathode. Whereas in full charge and partial discharge, we have incorporated 2 test conditions. One is like 100% of SOC charge and 80% of discharge, and 100% of charge and 90% of discharge. Whereas in the case of partial charge, full discharge, and partial charge, partial discharge, we have a different test conditions. So these all 9 test conditions will meet the requirement for the current EV applications, because if you can operate from 80 to 100% of SOC levels, which can actually enhances the driving range of their electric vehicles. So by designing these test conditions, here we can say the yellow one is like the unlithiation level of the cathode, which means only 80% of lithium we have utilized from the cathode, and then remaining 20% is charge we are left over in the cathode. We didn't cycle this 20% of lithium. So when the cell is getting aging, which means when the lithium ions are consuming in irreversible reactions, so the available lithium ions still can be participated in the electrochemistry, so it can enhances the cycle life. That is the basic idea of our design of experiments. And vice versa, in the case of partial charge and partial discharge, what we done was we have stored some extra charge in the anode as well as in the cathode. So during the electrochemical cycles, even at an interfaces of the anode or cathode, if the lithium ions are consumes, then the extra stored lithium ions can be participated in the electrochemistry, so which can actually enhances the cycle life. So if you can look at the right hand picture, these are the cycle life studies over the cycles. For example, we can say like the capacity retention from the first cycle to the like for example over the cycles for each test conditions. So for full charge and full discharge test condition, the cycle life was limited to only 900 cycles, whereas in other test conditions the cycle life number was increased tremendously. Even if you can compare with full charge, full discharge, it's almost 2 times for full charge partial discharge, whereas it is almost 3 to 4 times in the case of partial charge with the full discharge. Interestingly, the partial charge and the partial discharge was the cycle life showed in between the full charge, partial discharge, and the partial charge and the full discharge. But generally, in all electric vehicles applications, we will go with the partial charge and partial discharge. But if you can compare the cycle life, which is still lower than that of the even full charge and partial discharge. So this is one of the new invention in our studies. And again, if you can consider like one charge is for one day, like for 900 cycles, which means 900 days, which is almost equal to 3 years of lifetime. This is so in the case of full charge and partial discharge, it showed around 3600 cycles, which means almost 10 years of lifetime. And then whereas in the partial charge and full discharge, it has above the 10 years of the lifetime. So even we are charging at higher C rate, which means even less than or equal to 15 minutes of the charging, which is a demand for our EV applications. And these test conditions significantly shows the highest cycle life. But the range in terms of the range, if we can consider the full charge full discharge supposed to be gives a higher range, because the utilization energy density of this test condition could be higher than that of the other test conditions. But whereas the cycle life is very less, so if you can able to modify the test condition by mitigating the aging mechanisms, and then this test condition can be well suitable for the electric vehicle applications, and which is one of the current demand, like the range anxiety. One charge for for example 300 miles or 400 miles, that can be achievable by understanding of the aging mechanisms of these test conditions. So that is what our main interest of study for doing cycle life at different operating test conditions. And then to understand the main aging mechanisms involved in these test conditions, we have performed the non-destructive characterizations by using X-ray tomography analysis. So we can say this is a beginning of the life, uncycled lithium-ion cell. And when we have carried out the cycle life at a different test conditions, for example end of the life for the full charge full discharge conditions with the other six test conditions, we can see at the end of the life the electrode jelly roll completely deformed, and we can see there are many gaps were there. These gaps we can call it as a gas pockets, and then these gas pockets were formed due to the electrolyte evaporation over the cycles. As we can see here, over the cycles the cell temperature is also increases. So this cell temperature actually causes the evaporation of the electrolyte within the jelly roll, and then it can causes the this kind of deformation by forming the gas pockets. Along with the gas pockets, for this full charge and full discharge condition, so we can see even electrode deformations are occurred in the jelly roll. If you can compare with other test conditions, like for example which is the showed the highest cycle life, for example 3000 4200 cycles, which is more than 10 years lifetime. So the deformation is still very less. We can look at see 80 SOC and 100 DOD. The deformation is less compared with all other test conditions. And whereas the partial charge with the partial discharge, we expected this supposed to be the highest cycle life, which it shows the significant deformation in comparison with the partial charge with the full discharge, which is showed the highest cycle life. So these results are quite controversial each other, like controversial. So that's what we are trying to identify, what kind of even electrochemical aging mechanisms were taken place over the cycles. So for which we have carried out failure mode analysis. We have dismantled the cells after doing the non-destructive studies, and then we have identified that all cells anode morphology or anode structure was changed. We can see here, these are the optical images, we can say. So for the lower operating voltage and charge and discharge test conditions has showed the belt type of structure we can see here. So this color indicates the charge level of the electrode. So for different test conditions, we can see different color indications. Each color indications, as I mentioned, it shows the different lithiation level of the electrode. Whereas in the case of 80 SOC under DOD, which has showed the highest cycle life, and then the second highest cycle life, 100 SOC 80 DOD, these two test conditions, the anode degradation is a minimum compared with the other test conditions. Whereas in the case of 100 SOC 100 DOD, the electrode completely delaminated from the current collector, and it is sticked to the separator, which is one of the reason the cycle life was lower in this case compared with the other test conditions. So to understand further the electrochemical side reactions, we have done the SEM characterizations, and we can see here the SEM morphology studies reveals that where the golden color is there, which is electrochemically active. So in that zone, in that area, electrochemically active area, the more SA layer was formed, and where the uh, electrochemically inactive, so that area the morphology is completely changed. So, which is also clearly indicating that the non-uniform distribution of the charge actually hinders the rate performance of the lithium-ion cell. Also, which can causes the localized temperature heat generation, and which can causes the electrolyte evaporation over the cycles. That's why the deformation of the jelly roll we have identified. So to further understand the 100 SOC, 100 DOD test conditions, we have characterized the microscopy analysis for the both cathode and anode surfaces. Interestingly, the cathode surfaces have a lot of like cracks on the surfaces, and we can see there the electrolyte is also like wettability is also very less. And then that play means where the pitches were like this cracks were formed, that area mostly the electrode from the electrode degradation, means the cathode electrode degradation was occurred, and then that degraded material was dissolved in the electrolyte, and then it has deposited on the opposite side of the electrode. We can clearly see that the from the cathode the iron particles were dissolved and then deposited on the surface of the anode. So where the particles, where these cathode like a transition metal particles were deposited on the surface of the anode, that areas or that locations, uh, the SCA layer or the electrolyte decomposition also occurs, and which causes the continuous film growth on that areas. So which is clearly indicating that when the transition metal dissolution occurs, which deposited on the surface, which acts as a catalyst to decomposes the electrolyte continuously, and then forms the SL layer on the surface. So this SL layer, when it forms, it consumes the active lithium ions. So what happens is, as a result, the capacity fade will be accelerates. So this is what we have identified the effect, and this effect is due to the cell temperature rise. So if you can able to reduce the cell temperature rise over the cycles, then we can able to mitigate this aging effect. That's what our understanding. So how we can actually reduce the cell temperature rise over the cycles, for which we have defined the different test protocols. If we can look at here, at the up to end of the charge in a constant current mode, the current will be the same. It will be the higher, like for example, if you are working charging at the 4C rate, it will be almost a 10 ampere hour cell for a 2.58 cell. So if you can able to reduce, if you can design the protocol such a way that if you can reduce the end of the cell voltage current, so that if whether it can able to reduce the cell temperature or not. That's what our design, and then which actually showed the significant changes in the cell temperature rise over the cycles, and as well as the cycle life was increased almost 3 to 4 times compared with the conventional charge mechanisms. So this test protocol clearly indicates when we decrease the current pulse at an end of the cell voltage, which can actually reduces the overall the cell temperature rise by minimizing the internal cell resistance, and then it can allows the utilization of the active material from the cathode as well as from the anode uh, during the discharge process, so which can actually enhances the cycle life. So that's how we have implemented this test method to improve the cycle life. And with these findings, we have filed a patent recently, Indian patent we have done. So it is under review right now. And with that one, I would like to thank you everyone for attending this conference today. Thank you. If you have any questions, please. Yeah,
Yeah, thank you very much, Dr. Vallabha. Yeah.
yeah.
So now we are open to questions. So just a quick question. So when you talk about fast charging lithium-ion batteries, can it also have negative implications? Like can it increase the cell temperature or reduce the battery life as such in the long run?
Yes, that's what we have studied. Like for example, in our case, when we are operating the cell at fast charging, 15 minutes charging. So due to the cell internal resistance, the cell temperature was high. It increases. So which actually causes the electro degradation as well as electrolyte decompositions. So which actually resulted in the lowering the cycle life. So that's aging mechanism we have identified, and then we have modified the test protocol such a way that the cell temperature rise supposed to be reduced over the cycling without compromising the same charging time.
Okay, okay, thanks. Any other questions?
Yeah. Okay, Dr. Rao, I just have a quick question. So very nice presentation. I was
Thank you.
wondering, like, what is your opinion whether the optimization of parameters are important, or the search of new materials, like there are new materials, of course, which can also deliver fast charging, and at the same time they can also deliver high capacity, which is also required for you know development of batteries for EV and other high power applications. So
Great question.
what is your
Yeah.
take on this?
Yeah, great question. Great question. Yeah, really appreciate it. So these electrochemical reactions, even if you can develop the new materials which are capable for fast charging and longer cycle life, but the aging mechanisms, once it occurs, like for example, the cell temperature rise will occurs, the electrolyte decomposition and then delamination of the cathode materials, it will be the general phenomena even if you can do the constant current mode. But what we have understood or we studied is if we can modify the test protocol for any novel materials also. For example, it can gives the say x number of cycle life. By modifying this test method, that cycle life can be extended even further. So it can minimize the internal aging mechanisms even for the novel materials or new materials chemistries.
Okay, but
Yeah.
you also agree that the new material search is parallelly important, right?
Yes, yes, it is important. It will be important. Like for example, instead of like uh,
I think
if
the
you can,
neodymium titanate
yeah.
is one of the example, right?
Yeah, for example, if you can bring the new materials, if high energy density materials, then you no need to like high energy density materials means you can operating voltage means the utilization energy density even at lower potentials are also will be a good amount. So which means that you no need to operate the cell to fully charge and fully discharge in that conditions. So if you are not operating the cell to uh, fully charge and fully discharge, you can minimize aging mechanisms by introducing the high energy density materials and all. Got my point,
Right,
right?
right,
So
right. I
that's what
got
I,
it.
yeah, yeah,
Yeah,
that's what
it
I
makes
would like
sense.
to say. Yeah.
Yeah. Also, like I was, wondering, like the research what you're doing there, if it has to get translated to industries, like the terms SOC or DOD, these are the terms which are more relevant to researchers working in the field. But I think there has to be parameters in terms of maybe the cell voltage or something which is a consumer can understand, I would say.
Exactly correct, right? That's true. Like we are now working towards the like up for higher applications, for example EV applications and all. So like for battery management designers, they needs mostly like SOC and the DOD terms. Like for layman, as you correct, we need to tell them like what operating voltage like if we have to provide the operating voltage ranges. That is absolutely true. And like very soon, I think we are now working on we are implementing these protocol for high end applications, especially for electric vehicles fast charging. So
Right.
yeah.
Right. Thank you. Thank you very
Yeah,
much.
yeah, yeah. Thank you.
Any more questions?
So
Yes, yes. Please.
nice to hear, Dr. Rao, a good way of looking at things in the terms of more towards putting a criteria for understanding the battery.
Right.
But every material has a different chemistry. For example, if I go to LiCuO2, probably there we are unable to take the full discharge, even in
Right.
any condition, because the
Right.
material limits. So
Yes.
these conditions that are maybe very valid for LiFePO4 probably may not be good price for any other system, right? So is it like a material specific strategy to adopt, or like we should have some generic strategies that can be useful for all sort of materials?
Yes, actually, we are trying to implement this protocol for all chemistries. Like here, the full charge, full discharge, when I'm mentioning, it is not completely delithiating or lithiating from the active materials, like from the different chemistry of the materials. The full charge means it stands for what maximum level we can extract the lithium from the chemistry of the materials, so that we can consider it as 100% of SOC. Like experimentally, how much lithium we can extract from the we can remove from the materials, that limitation we can consider it as 100% of SOC, which is
But that,
like
yeah, so that is what I understand, but that is also a material specific.
yes,
LiFePO4 gives me liberty to extract 100% lithium.
yes, yes,
When it doesn't go bad if I take 100% lithium out and put in.
yes,
Whereas
yes,
in case of LiCuO2 or some other components, especially those are manganese based, where John Taylor distorsons are more prone, right?
absolutely correct,
So they
yes.
are taking 100% means you are going to destroy your material and ending up with a new problem.
Right,
So for
right,
that, material is limiting to extract 100% lithium. So
correct.
probably then the criteria may be something like to an extent where probably the material is not going to degrade.
Yeah, yeah.
So
Yeah, that's a good suggestion. Yes, like we can consider, like for example, from LiFePO4, 100% is lithium we can extract. That is considered as a full charge. For
yeah,
example, for LiCO2, for example, only zero point 0.8 means 80% of lithium only we can extract to maintain
I
the
think that is
structural
also on the
stability.
higher side.
Higher
Yeah,
side. So that
yeah,
higher side we can consider it as a we can consider it as a 100% of state of
yeah.
charge
So
experimentally. So these
experimentally,
tests
so
yeah,
probably the limit on lithium should be put, I think, based on the material to material, rather than
yes,
calling it at 100%. 100% of that material's specific capacity that can be extracted.
extra, yes, exactly correct. Yeah, yeah. Thank you. It's a great suggestion also. Yeah, thanks.
And also when you do this topographic X-ray topography measurement,
Yes.
right? So like what is the energy of these X-rays that you use?
Here we are using almost, I can, if I remember correctly, 20 kilovolt. That's what we are using.
Mhm.
It's a nano resolution one. As you are there are different resolution tomography CT scans are there. So I think we have used high end CT scan, which is functioning at 20. The beam energy is around 20 kilovolt, I believe. Yes.
But in that case, you may not have resolution to a nano, but you may have resolution to micro.
Micro. Yeah, we are getting. That's why we are getting micro size actually. That resolution will tell nano, but because of the size of the sample, the resolution, again, the image resolution varies actually.
Okay, and how many
Yeah.
scans that you do across the sample? For example, this
Uh,
is a cross-sectional scan.
yeah.
In vertical sides, for example, you show the cylindrical cell. Suppose if I
Right.
consider the cylindrical double A cell or triple A cell, what
Right.
are the scans that you add up to final image?
We have done almost 1,000 scans, like across the like vertical from the top to bottom, and then
And then
we have,
integrate them.
yes, we used to
Okay.
integrate them. Yes. Yes.
Okay, fine.
Yeah.
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 Can this also be implemented on a laboratory scale like coin cells or something, this topography that you have?
Yeah, we can implement. Yes.
So
Absolutely.
their cell casing may not be a problem because in coin cells usually SS is
Small
used.
scale. Yes. It can easily penetrate. Yes.
Okay.
Yeah.
Okay, thank you.
Yeah. Thank you so much. Yeah.
So what is the Dr. Rao, what is time at your end?
Now it is around 8:20 a.m.
Oh, okay, so it is manageable, not too early.
Yeah. No. Yeah.
Good.
Yeah, so if there are no more questions, I think let us thank today's speaker, Dr. Vallabha Rikka, for sharing his insights on the emerging area of lithium-ion batteries and the challenges being faced. So once again, thank you very much, Dr. Rikka. It was
Thank you.
great to have you as one of our speakers at the CTFP webinar series. And so with that, I think we can end this session. And thank you all very much for joining today's webinar. And have a nice day.
Thank you. Thank you, everyone. Yeah.